So we ended the last video talking about comparing two population means, and we looked at this printout here, and we realized that it may be a little bit more tricky than we imagined, because it's not just like a test statistic and a p-value, and hey, let's go ahead and do it. And one confidence interval, we can see there's a couple different sets of information. And I opened up the can of worms and said there are different ways of estimating variances, and I'm actually going to talk about 3 scenarios. And the 3 scenarios are really because of these unknown variances. Both this is the confidence interval here on the left, the test hypothesis formula on the right. This is how the computer is doing the math in this printout. And regardless of whether you're doing a confidence interval or a test hypothesis, there's going to need to be some estimation of these population variances. The sigma 1 squared, the sigma 2 squareds that you see represent variation in the data in the population. So if you're comparing the GPAs of males and females, sigma 1 squared refers to the variation of the male GPAs. Sigma 2 squared refers to the variation of the female GPAs. And we need ways, or we need to think of how that's going to take place, how we're going to do that estimation. One size doesn't fit all, unfortunately. And the 3 scenarios, the first one is the easiest one. The first one is if we take large samples, and again, in this section, we said a large sample is when both our sample sizes, N1 and N2, are greater than or equal to 30. Again, a big cautionary statement here. Sample sizes are not always 30 or more. That is not necessarily a criteria we use to determine whether large or small samples. It works here early when we're working with means. Single mean, we need N greater than or equal to 30. Comparing 2 means, we need both N1 and N2 to be greater than or equal to 30. So that's how we're going to judge whether we have a large sample. You can see in this printout, my sample sizes here are not large. So that wouldn't apply to the example I kind of threw up here to start us having this conversation. But if we did have large samples, here's the thought process. If we have a large sample, my first sample variance does a good job of estimating that sigma 1 squared, and my second sample variance from, again, a second large sample does a good job of estimating sigma 2 squared. So large samples, individual sample variances, the S1 squared and the S2 squared, can just get plugged in, and that's what the computer's going to do. Now, the way that the software we're using here, the statistics software, works, there's 2 rows here, and you see the variances, you see the statement here, there's equal and unequal. I wish there was a third one. I wish, because there's 3 scenarios, right? I wish there was a third scenario that said large samples, and that there was another row of information underneath here, and I would say just go ahead and use that. Because in reality, I would like to say let's go and use the large sample estimation, and let's go ahead and use a z-distribution. Well, statistics doesn't give us that option. And so the best thing we can do, and I'll do it this way, the best thing we want to do is we'd use a z-distribution. Statistics doesn't give us that option, but the best option available is to say, if we have large samples, let's go ahead and use the unequal row. Now, the unequal row in statistics will use the t-distribution. We really want to use the z if we have large samples, but that's the best option we have. And really, when you take large samples, the t-distribution and the z-distribution are going to be pretty close together, and so the difference is going to be negligible. So if we had large samples, I say let's go ahead and use this unequal row. Here's the p-value that we would grab off it. Again, this would be true if we had large samples. We don't in this case, but I'm just kind of showing you where the information is located at. And if we were doing confidence intervals, we'd look at these endpoints right here. You can see they're both negative numbers, and we would make our appropriate conclusions. So working with large samples is straightforward. We know what to do. Working with large samples is straightforward. I'm smiling right now because I know the conversation I'm going to have with you here in a second. Working with small samples is not. Okay. When we're working with small samples, again, let's think about the conversation we're having here. We're trying to estimate these sample variances. In one case, you can plug in the individual values of S1 squared and S2 squared. That makes sense when you have large samples. But what about small samples? Well, originally, we always just plugged in S1 squared and S2 squared and said that's it. But then someone came up with a better way, and my students always hear me say this. There's an ugly word in life, but also in statistics, and that word is options. And most of the time when you think about options, you think, that's great. We have options. We have different ways of doing things. It is good. And we do get better information because of these options. And ultimately, that's a good thing. The problem is it's also a complicated thing. Now, what do I mean by that? Well, I could plug in the individual sample variances S1 squared and S2 squared. If I have small samples, everyone recognizes that, with small samples, those sample variances may not do a great job. They may not estimate the population variances all that well. S1 squared may not be a great estimate of sigma 1 squared. S2 squared may not be a great estimate of sigma 2 squared. I wish there's a better way. Well, follow me here. The example I've been talking about has been GPAs, right? I've used that a couple times. I've talked about that. Compare the average GPAs of males and female students. Now, imagine, if you will, taking all the male students at a particular college or university. Okay, so think about your school. Take all the male students. There's a bunch of them, right? But take them and sit them in, go to a stadium. Say, all right, there's a mandatory meeting. All the males have to go to a stadium at a certain time. So you get every single male who's attending the college to sit down in the stadium. Now, if you think about it, if you will, think about the GPAs of those students. Okay? As you look at those males that are sitting there in that stadium, what's the highest GPA represented? Easy question, right? The highest GPA is going to be 4.0. And there's going to be a certain number of male students that have the highest GPA of 4.0. What's the lowest? Now, it's usually tempting to say 0. But let's think about it a little bit. Can you really have a 0 GPA? And you might be saying, yeah, you can. But can you have a 0 GPA for a period of time, for a long period of time? And the answer is no, you can't. Because if your GPA is 0, what do you become? You become a former student at that point, right? And so as you look at the vast majority of the students that are sitting there, the male students that are sitting there, their GPAs are going to range between 4 on the high end and probably around 2. Because once your GPA dips below 2, you're on a limited time basis. You're going to be asked to leave shortly. And so most of the GPAs are between 2 and 4. The average is somewhere around a 3. Okay, that's what my experience has shown over the years, slightly higher than a 3.0. But that's what the male GPAs look like. And there's some variation in there. Okay, they're not all the same GPA. There's a variation. Now, have the same conversations. Do the same thought process about the female students at the same university. Aren't you going to say the same thing? Aren't you going to say that the female student's high GPA is going to be a 4.0, the low is probably going to be around a 2, and again, there's some lower than that, but they're not going to be here long. The vast majority of females are between 2 and 4. The average is also somewhere around 3. But here's my point. In certain situations, and the GPA example is an easy one to think of, and it's one that you guys are probably very familiar with. In certain situations, the variation in the first population and the variation in the second population is going to be the same. Okay, let me say that again. The variation in the observations in one population is going to be identical to the variation in the observations in the second population. GPAs is just an easy example. The variation in male GPAs, how much they vary from one male student to the next, is probably the same as the variation in the female GPA. And it's primarily because of the data you're working with. GPAs are between 2 and 4. They're kind of restricted in there, aren't they? And so in that situation, here's the thought process. If you have two populations that have the same variation, rather than use your small samples to estimate sigma 1 squared and sigma 2 squared separately, don't plug in S1 squared, don't plug in S2 squared, but you plug in what's called SP squared for both. Now, there's a whole lot of math going on behind the scenes that I'm not going to show you. I just want you to have the thought process down. Rather than use two small samples to estimate the individual variances, take those two small samples and combine them and think of one sample. Then you use that estimate for both. So take the male's GPAs and the female GPAs in your small samples and put them together and look at say you had 10 males and 10 females. Rather than using two small samples of 10 and 10 to estimate these individual sample variances, it's saying put those observations together. Use a sample of 20 combined, and the P stands for pooled. Pool that information together, do some math, and the computer will do it for us. But use the one sample of 20 as an estimate for both. That sample of 20 will be better than the individual samples of 10. Options. Ugly word, options. If the population variances are equal, it makes sense to do that. So first scenario, you have large n's. That's really easy. We're just going to use the equal, or excuse me, we're just going to use the unequal row. Small n's, if the population variances are equal, we're going to assume that we're sampling from normal approximation or approximately normal populations. Why? Because we have small n's. If they have equal variances, we're going to assume that the variances are equal, and then we're going to use the equal row. We're going to come in here and get what's called the pooled method. We're going to use the equal row on the printout. We need approximate normal populations. We need equal variances. The third scenario is what happens if you have small n's and the variances aren't equal? The unequal variance, well, then we're just going to have to assume that both populations are approximately normal and use the unequal option. The only time we have to go through this stinking thought process is when we have small samples. Large samples are easy. Small samples, a little bit more complicated because we have options. Almost think of it as good, better, and best. Best is you take large samples, you don't have to worry about it. Good is you have small n's. Use unequal variance. Better, if you think the variances are equal, use the equal row. Think about your data that you've collected for me this semester. Yeah, you're probably going to have to go through this, aren't you? You don't have large samples. You don't have two samples that both have 30 or more. How do I know that? Because I forced your hand. I'm going to force you to use small samples and go through this thought process for me. It's not that tough. It sounds tougher than it actually is. Okay. Now, a great question is, all right, GPAs, that makes sense that they would have equal variances, but how do I know? How do I know in my data set if the two levels that I'm working with are two, and typically I have you collect 3 levels, right? And for this analysis, I'm going to say just use 2 of them. How do I know if the variation in the prices in the one level are going to be the same as the variation in the prices of the second level? And so we need to have some way of determining if the variances are equal. Well, you can see I've been spending a lot of time here, but there's another piece on this printout down here. And so let's go to the next slide and take a look. Determining if the variances are equal. Now, this semester we're going to spend a lot of time looking at means. We're going to spend some time looking at proportions. We are not going to spend time looking at variances. That's what you'll hear me say. However, before we can compare the means, and again, if we're working with small samples, before we can compare the means, we have to look at what's the relationship of the population variances. Are they the same or are they different? And right now, I'm looking at this part of the printout. The very bottom part of the printout here is doing this for us. And back in the day, we'd have to learn about the F distribution because that's what it uses. It's called a folded F test here on the printout. But the null hypothesis says that the variances are the same. The alternative says they're different. If P is low, and I'm going to have you use an alpha 0.10 whenever you're doing a variance check. If P is low, we reject the null hypothesis. If P is low, and the P I'm referring to is this guy right here. If P is low, we reject the null. We reject that the variances are equal. If P is low, we're going to say the variances differ. They're unequal. If P is low, we use the unequal row. If P is high, we fail to reject. There's insufficient evidence. We can't say the variances differ. We can't say they're unequal, and so you use the equal row. When you have a small sample size, that's the only time you need to come down here. If one or more of your sample sizes is less than 30, this p-value indicates which row here. That's a terrible looking parenthesis. Indicates which row you should use. You can see in this particular printout, it isn't going to matter because my p-values and my confidence interval endpoints are going to give me the same interpretations regardless. Will there be printouts where it matters? Yeah, sure, of course. Is it going to be yours? I don't know. Usually when I have classes of 140-ish students, there might be 5 to 10 of you where it'll matter. When I write exams, now it's up to me. Now I can give you any printout I want. But when you're working with your data sets, I don't know. Most of you guys, it won't matter. But for some of you, it will. And so I want you to do it right. When you have large n's, use the unequal row. When you have small n's, you got to take a look at the variances first. And we do it through this p-value right here. We interpret this p-value just like every other p-value. That's why I don't care so much about the F distribution. You don't need it. When P is low, you do need to know this. You always need to know what it is you're testing, and you need to be able to interpret p-values for me. We get the p-values from the printout. It's a great example of that. Completely new scenario. Kind of came from left field here. Where'd this come from? Just out of the blue. But you know how to do it. You know how to interpret p-values, or you should. It's a skill you need to do. So that's how we determine what we're doing. All right, so that's a lot of words, and I'm looking at my video now. I'm over 15 minutes into this video. I'm going to cut it off. And now we're going to take a look in the third video of this sequence or this section. We're going to take a look at a third video of how we actually do it. And what I think you're going to find is it's probably going to take us longer to talk about it than it will to actually do it. So take a break, come on back, and we'll take a look at a couple examples where we see how to do this. So long.